Hi guys, we had a knowledge about Faraday's laws of induction, electromagnetic induction. So this law says that the EMF E induced in a circuit is directly proportional to the time rate of change of the magnetic flux through the circuit. So as a formula we can write that EMF E equal to negative of d phi suffix b by dt. So here d phi by dt is nothing but magnetic flux. So that goes as BA cos theta. Here very important thing is that the negative sign. So today I am going to talk about this negative sign. It is tricky but it is easy. Here the negative sign shows that the induced EMF and the change in the magnetic flux, they both are having opposite sign. So to know about the negative sign, we need to know about Lenz law. So Lenz's law says that the induced current has a magnetic field. Yeah, we know that a current carrying element gives a magnetic field. Even though it's induced current carrying element, yeah, it contributes magnetic field. So the induced current has a magnetic field that opposes the original change in the flux through the area enclosed by the loop. So it is a little tricky as a definition when it comes, but try to get it carefully. Since the induced current has a magnetic field, okay, till that, and magnetic field comes with poles. Yeah, it comes with two poles, north and south pole. And the poles, they develop in that current carrying element such a way like that. So they opposes the original change in the flux through the given loop of area. So the opposing nature only we are representing with the negative sign in the Faraday's equation. So this law is given by Lenz. So let us try to apply that. Suppose you have a loop, a current carrying loop. So this is the current carrying loop. Now to this loop, you brought a bar magnet. You are moving a bar magnet close to the loop. Suppose you take first, no current, nothing was there. It's just an ordinary loop. Now if you bring close to a bar magnet, close to that, means this is the moving direction. And so this is the north pole of the bar magnet. So it's contributes magnetic field lines. Suppose these are the magnetic field lines. So they are passing through the loop. Now because of these magnetic field lines, in this loop current, induced current comes. Now that induced current causes magnetic field. Okay. Now, here the problem is that what is the direction of the induced current? So the direction of induced current in the loop is in such a way like that. The induced current should develop a magnetic field in this loop. So that magnetic field should oppose the original magnetic field. So here it is the original magnetic field. So here it is the original magnetic field. Now to this original magnetic field, the current, it will develop in a anti-clockwise direction in the loop. So this is anti-clockwise direction. Because of the anti-clockwise direction in the loop, if I take it out these magnetic lines, then it's easy. So in the loop, it will develop a north pole. So you can follow the arrow mark. So north is having the same direction of the arrow marks in the loop. Now this loop in this side contributes north pole. Now we know that one, these two north poles, they will repel each other. So when a bar magnet of north pole moves towards to the coil, a loop, so in that loop current will be anti-clockwise direction. The anti-clockwise direction current contributes north pole. And we know that when bar magnet move away from the loop, when it is moving away from the loop, it means magnetic field lines are moving away. So in this case, when the magnetic field lines are moving away, again induced current changes in the loop. Induced current direction. Induced current direction changes. Why it is changes? Because it is always opposes the original change. Now this case, in the second case, when the bar magnet moves backwards, it means magnetic flux is decreasing. When the magnetic flux is decreasing, now this times the current in the loop develops in clockwise direction, so that the clockwise current in the loop contributes south pole. Now the south pole wants to attract north pole of the original magnet. So in the above case, when north pole comes towards to the loop, now induced current wants to oppose it. So that's why the current will become anti-clockwise direction, so that it can develop north pole. So north and north will repel each other. But in the second case, when bar magnet is moving away, so north pole is moving away, but induced currents wants to oppose. Since it is going away, it wants to attract. So the induced current will develop in the loop such a way like that. It creates south pole in the loop, magnetic south. So for that, the current should be in the loop will be clockwise direction. Now I will encourage you remember in the loop, if current is clockwise direction, so that contributes south pole. In the loop, if the current is anti-clockwise direction, that contributes north pole. Now let us apply the case to it here. Suppose if a bar magnet is approaching towards a copper ring, let it be a copper ring. Copper is a conductor, a copper ring. So magnetic flux is changing. So when the magnetic flux is changing such a way like that, with respect to coil, so in the coil induced current develops. So here I is the induced current. But what is the direction of induced current? So the induced current will flow in such a way direction that contributes an opposite pole. So it means here the magnetic field lines are approaching. So now it should be repelled. Now in the second figure, B figure, if you can see, so the ring one side having north pole at here and another side is south pole. Here the current direction, if you can see, the current direction it is going anti-clockwise direction. So when north pole of a bar magnet is approaching towards that one, the current in the copper ring is anti-clockwise direction. So the anti-clockwise direction contributes north pole. So here, so magnetic north pole will develop. So these two north poles will repel each other. So that is the opposing. But when you can see the second case, when bar magnet is moving away, it means magnetic flux lines are moving away. Now north pole is moving away. Now current in the copper ring will change its direction because it supposed to oppose it. Now north is moving away. Now it should be develop a south pole so that it can oppose the south. So when it comes to south, so this is S, we can write like that. So it means the current in the loop is flowing now in this clockwise direction. So this is the magic of the induced current direction, which is given by Lenz. So try to draw the current direction in the given circuit. So if this is south pole, which is approaching towards to the coil, now current in the coil will develop such a way like that. So if I can draw S in the coil, so because it needs to oppose it. Now the arrow marks will be in the letter S will be like that. The same arrow marks I will give to the loop. So when you look from the magnet side, so the south pole and south pole will repel each other. Now the current in the loop will be clockwise direction. Suppose when you change the loop to different. Now here I have taken a rectangular conductor, a copper rectangular conductor, which is kept in a uniform magnetic field. So to get the completion of the circuit, so here it is one more conducting rod, which is also a conductor, so that these two copper rods are connected. Now what we learned that? We learned that a change in the magnetic flux, causes current. Okay, so when I move this conducting rod, if I can call this as AB, if I move the conducting rod towards to the right side direction. So when this conducting rod moves, if you can see, there is a change in the magnetic flux. So the magnetic flux with this closed loop, now this will be acts like a closed loop. So this closed loop, with respect to closed loop, the magnetic flux is changing. So the direction of current, from A to B, if you can take like that. Now when you move in opposite direction, now this is the movement direction. Again, now if AB is the conducting rod which kept on that two copper rods, now when you move again, there is a change in the magnetic flux. Now in this direction, in this case, again the current direction will be changes. Now depends upon the direction of the movement, that causes change in flux. Now the change in flux causes induced current, and that induced current always opposes the original change. Now let's try one more example. Now this is an electromagnet. As usual, same, if a solenoid which is connected to a switch, here switch is off, so there is no magnetic field, there is no induced current. So in this case, no induced current. But when switch is on momentarily, when switch is on, so we know that a current carrying solenoid acts like a bar magnet. So if you can take, this is a south pole and this is north pole. of a bar magnet and hypothetical. So these are the magnetic field lines. So they are moving in the direction like that. So if this side south pole contributes, now the induced current will develop in the copper ring what you kept at here. So it is also contributes south. Why? Because it always should opposes to the original. Now that's why the current flows in the copper ring in the clockwise direction. So this takes momentary, spontaneous. But when you can switch off, now in this case, now the third case, if you can take when the switch is off, and this is also momentary. So when switch is off, it means magnetic field lines starts to decrease. Now by the time, so the flux decreases. To oppose the flux, to oppose the change, the induced current, it changes its direction. Now in this case, the copper ring current flows again in the anti-clockwise direction, that contributes magnetic north. Let us try to apply this same for certain given cases in your exercise. Now the question is, predict the direction of induced current. Now this is a bar magnet which is moving towards to the coil. Suppose when you are looking from the axis of the bar magnet, so you are looking from that direction. Now this is magnetic south. Now here the same south pole has to develop. Why? Because the induced current develops such a way like that it should opposes. So it should opposes because south pole is approaching towards the coil. Now in the coil, the south pole should come. So to form a south pole at here, so the induced current will flow. So the induced current will flow in the clockwise direction. You remember that clockwise contributes to south and anti-clockwise contributes to north. Now since it should form south at here, now the induced current flows along clockwise direction. So if we can give the clockwise direction, so this is the direction of the clock which is flows. Now I can say the induced current is flowing from along the same the direction. So the current will be the flows along at here. So Q R P Q. So that is the direction of induced current. Yeah, that gives to us clockwise direction R P Q. So here don't be confused, the clockwise direction of in the external circuit and the clockwise direction in the loop. Where do you need to see that? So you need to see that in the loop itself. So this is the loop of the south pole it is contributing. Now if the south, if I draw it here, the same line I need to draw in the first loop of that one. So the current direction will be the flows in this direction to that. So now if you can check the answer at here, now it will matches. So now the current direction from the Q R again P to the Q. Now that is the direction of induced current. What if the bar magnet moves such a way like that between the two coils? Let me take one more example. Yeah. Now in this case, the bar magnet is moving between two coils. So what is the direction of induced current in the coil 1 if I can talk, and the coil 2 if I can talk? If I take the second coil. So we know that if the south pole is approaching, so here the south pole should develop. So to develop the south pole, so here the Q is the last portion of the ring. So the same Q, from the Q current should be passes to the last pole. So sorry, the last loop. Now what is the direction of current? The direction of current in this case is from the P R Q. That is the direction of current, because from the Q only the current should enter in the last loop. Now if you can draw the S at here, so that is the same direction of the current, so that gives the clockwise direction. Now when it comes to second coil, the north pole of the bar magnet is moving away. So it means here the induced current develops such a way like that it should contribute to the south pole. So in this side the south pole should come. So if the south pole should come, what is the direction of current at here? To get that, I can take the help of another. So if it is south pole, by common sense this contributes to north pole. Okay, so if it is the north pole, now if you can take the same direction of current at here, now the last string is touching at here. Now if you can draw the arrow marks as it is like this, now I got it. The current is flowing from the Y to Z and Z to X. So that is the direction of current in the second coil. So try to apply it carefully, particularly the direction, don't get confused. Always think about the induced current always opposes the original change. Let us try to apply another case. Suppose this is the case, predict the direction of induced current. So tapping the key just closed. So as the current in the left loop is completed, the current flows in the direction of the arrows as shown in figure. This current is developing, I think, is south pole. Yeah, if you can draw as at here, the arrow marks are shown same at here. So this is contributing south pole. So the current develops south polarity on the side of the right loop. Now the induced current should flow in the another loop that is also in the same clockwise direction, because if it's south pole, if you can take first loop and the second loop, in the first loop it is south pole, in the second loop also it's supposed to be south pole, then only it's supposed to be opposites. So to get the south pole, the current should flow in the, first I draw the south pole, then after I can draw the current direction, the current should be in the clockwise direction. So if you can write that the current is flowing along the direction of current X to Z to Y. So this opposes the growth of the current. So the direction of current X to Z to Y. So when you look from the left of the loop, so the induced current always opposes the original magnetic field. So that's the way we need to apply the same at here. Try to do more analyze, so then you can get better knowledge. Now let us try to apply last case at here. Suppose when the rheostat setting being changed. So what happens if we change the rheostat settings? That increases current in the circuit. As the rheostat is adjusted, so the resistance decreases and current increases. This increasing current causes increasing the flux in the neighboring coil. Suppose if it is the coil 1, if the coil 2, if current in the coil 1 increases, the flux in the coil 2 increases. So by Lenz law, it says that the increasing of flux should be opposed. Now the induced current should produce flux in the opposite direction of the original flux. So in the original flux, find the polarity of the magnetic field depends upon the direction. Suppose it is showing in the anti-clockwise direction. So if it is anti-clockwise direction, here it is contributing north pole. Yeah, anti-clockwise direction is contributing north pole. So the same north pole should be developed in the another coil so that it can opposes. So if we can put that north pole at here, the same, and you can give the directions. Now if you can take the arrow marks along this direction, now the current is flowing from the Z to X to Y.